Thanks for joining. This will be the first part of our Lintel series on principles of flexure. And to talk about principles of flexure, we will first look at a concrete beam and compare it to a masonry beam. My name is Phil Ledent, and I represent the Masonry Institute of Michigan. So for a concrete beam, we will draw our stress and strain diagrams according to provisions in ACI 318. So we will have a line at the top of our beam, a line at the centroid of our reinforcement, and a line at the bottom of our beam, and then draw our stress and strain diagrams and compare these to a masonry beam shown below. So we'll draw our strain diagram first for concrete. And so our strain diagram, from Hooke's law, that stress is proportional to strain. And so this will be our strain diagram. We have a D dimension, which is from the top of our beam or our maximum compressive strain to the centroid of our reinforcement. So this would be D as shown on the screen. And we know we have a neutral axis where our strain is equal to 0. And so we can draw in our neutral axis, and let me pull out a ruler so it's a little bit cleaner here. And so this would be where our strain is equal to 0, and this dimension from our compressive stress to our 0 strain point or our neutral axis is called C. In our strain diagram, we have a maximum usable strain of our concrete of 0.003, and so we know that point. And we have a point down here, which would be our strain of our tension steel, usually abbreviated epsilon sub T. And so that would be our strain diagram. As we look at our stress diagram, so if I extend this line out a little bit here to our stress diagram, and stress is abbreviated as thus. We have at the bottom of our stress diagram, we know that concrete has cracked in our ultimate state, and so we have the tension being resisted entirely by our reinforcement. So we have this tension force, T sub S, and that's going to equal our area of steel, A sub S, times Fy, our yield stress of our reinforcement. Our compression block, we idealize it as a rectangular compression block, and the width of it is 0.85 times F prime C, our specified compressive strength of concrete. So this is 0.85 F prime C. We know this dimension is A, the depth of our stress block, and we know it goes into the page a B dimension where B is the width of our beam. And so in this case, this would be our B dimension, 12 inches. And so if we take the area of that rectangular stress block, that then becomes our compression force in our member, which we abbreviate C sub C, and we would have 0.85 times F prime C times A times B. And so these would be our internal forces on our concrete beam member. And we have an internal moment arm equal to D minus A divided by 2, because again, we have a rectangular stress block in the top, and so the centroid of our compressive stress block would be A divided by 2. And so how are A and C related? Well, in concrete design, A is equal to beta 1 times C, and beta 1 is a factor of our compressive strength of concrete, and it's equal to 0.85 for F prime C, our specified compressive strength of concrete, less than or equal to 4,000 PSI. And so that's how A and C would be related. So we have 3 equations we can get from this. So 1, we'll set tension equal to compression because we have to maintain equilibrium within our member. So second equation we get would be AS times Fy, our tension force, has to equal 0.85 times F prime C, which is our specified compressive strength, times A, our depth of our stress block, times B, the width of our beam. And so if we solve this in terms of A, our depth of our stress block A equals AS Fy divided by 0.85 F prime C B. And our third equation we can get from these diagrams is our moment capacity. So our nominal moment capacity, M sub n, equals either our tension force or compression force, because we have equilibrium, times our moment arm d minus a divided by 2. And usually it's easy to solve for our tension force. So AS Fy times d minus a divided by 2 is our nominal moment capacity of that concrete beam. To solve for our phi factor, because ACI is based on strength design, we have to know if our section is tension or compression controlled. And if we are tension controlled, we have a strain in our reinforcement greater than 0.005 at the point when our concrete reaches its maximum usable strain of 0.003, and that gives us a phi equal to 0.90. If we're compression controlled, our phi factor equals 0.65, but ACI tells us that the strain in our beam always needs to be greater than 0.004 for flexural beam members. And so they're not allowed to be entirely compression controlled. They have a cap on the minimum strain you can have. And if we look at this in terms of yield strain, so our yield strain on grade 60 reinforcement from Hooke's law is going to be our strain, or our stress at yield divided by our modulus of elasticity. So for grade 60 reinforcement, we'd have 60,000 PSI divided by 29 million PSI. And so our yield strain for grade 60 reinforcement is 0.00207. So if we want to think about these strain values as a function of yield strain, for a beam even to be allowed to be designed according to ACI 318, we need a strain greater than 0.004, which is about 1.93 times our yield strain. For it to be tension controlled, we have to have a strain greater than 0.005, and that's about 2.4 times our yield strain. For it to be tension controlled, and again, if it's tension controlled, phi equals 0.90. Most commonly, we use similar triangles to determine our strain in our reinforcement. And so we have a known value of our strain in our concrete, maximum usable strain 0.003. We have a C dimension here, and this would be D minus C. And then this would be our strain in our tension steel. And so if we set the legs of our triangles equal to one another, since they share a vertex, we have strain in concrete over C equals the strain in our tension steel over D minus C. And so therefore our strain in our tension steel is going to equal our strain in our concrete times D minus C divided by C. And so we can solve directly for the strain in our tension reinforcement and compare it to 0.005 to see if we are tension controlled. If we're less than 0.005, we have to be greater than 0.004, and we'll have a phi factor less than 0.90. And so that's a brief refresher on concrete design, concrete beam design. So let's see how masonry compares. So if we have a CMU lintel or CMU beam shown here, and we draw our stress and strain diagrams, I'll use blue ink for our masonry beam. We have a line at the top of our beam, a line at the center of our reinforcement, and then we'll have a line at the bottom of our masonry lintel down here. And so if we draw our strain diagram, TMS 402 in chapter 9, which is strength design, tells us exactly how to construct our stress and strain diagrams. So it says strain compatibility exists between our reinforcement, grout, and masonry. In C, it tells us our maximum usable strain at our extreme masonry compression fiber is 0.0035 for clay masonry and 0.0025 for concrete masonry. And strains in reinforcement and masonry are proportional to our distance from our neutral axis. And so similar to concrete, we have a strain diagram that is proportional, and it looks like this. And we know that this point here, if we have a CMU lintel like we have shown on the left, equals 0.0025. And so comparing that to concrete, we had a maximum usable strain of 0.003. And so we can see that the materials are somewhat similar. We have a neutral axis that occurs at a point where we have 0 strain. And so we can draw this in here as well. And in concrete, similar to in masonry, we have a C dimension, which is the distance from our maximum compression strain to our neutral axis. And that tells us this down here, the distance C from the fiber of maximum strain to the neutral axis shall be measured perpendicular to our neutral axis. And so we have that, and we have our strain in our masonry, and then we have our strain in our tension steel down here below. And this would be D from the top of our beam to the centroid of our reinforcement. And so this would be D minus C, this dimension. All right, so that's our strain diagram. As we look at our stress diagram for masonry, similar to reinforced concrete, Chapter 9 of TMS tells us that we are not allowed to use any masonry in tension. So in F, it tells us masonry in tension does not contribute to axial and flexural strengths. Axial and flexural tension stresses are resisted entirely by our steel reinforcement. And so in our stress diagram here, on the bottom where we're in tension, we have this tension force, and our tension force equals AS times Fy, which is the same as it is for concrete. Above our neutral axis, we have a rectangular stress block of masonry in compression. And again, it goes B dimension into the page, where B is the width of our masonry beam here. And so on the magnitude of our rectangular stress block, if we look at TMS 402, tells us a masonry stress of 0.80, F prime M is uniformly distributed over an equivalent compression stress block. And so we know that this width here is 0.80 F prime M. And we can compare that up above to ACI, which we're allowed 0.85 F prime C. And similar to concrete, we have this dimension here equal to A, and A equals 0.80 C for masonry. So in concrete design, we have a beta 1 factor. In masonry, A always equals 0.8 or 80% of our C value. And so based on that, we can come up with the same types of equations here. So one, we're going to set tension equal to our compression force in masonry. And what is our compression force in masonry? Well, C sub M is going to equal 0.80 F prime M times A times B. And our internal moment arm is the same as it is with concrete, D minus A divided by 2. And so setting tension equal to compression, our second equation here, we would have AS Fy, our tension force, equals 0.80 F prime M times A times B. And solving that for A, the depth of our rectangular stress block, we get AS Fy divided by 0.80 F prime M B. And so virtually identical to our ACI 318 equation for concrete. The only difference is this factor in the denominator. So then we can calculate our nominal moment capacity of our masonry beam the same way. So our nominal moment capacity would be either our tension or compression force multiplied by our internal moment arm, D minus A divided by 2. And if we solve that for tension, it would be AS times Fy, our yield stress, times D minus A divided by 2. So it's virtually the same exact equation as for concrete design, just a few different factors. As far as our phi factor, so instead of addressing compression controlled sections with a variable phi factor, like what ACI 318 does, TMS 402 tells us we have a minimum amount of reinforcement and a maximum amount of reinforcement. And so our minimum amount of reinforcement for a masonry beam, our strain and our reinforcement, we can draw it up by our strain diagram. Strain and our tension steel reinforcement needs to be greater than or equal to alpha times our yield strain. And alpha for beam design, for lintel design, is equal to 1.5. So our strain and our tension steel needs to be greater than or equal to 1.5 times our yield strain. And what is our yield strain? Well, if we're using grade 60 reinforcement, again, we'd have 60,000 PSI divided by 29 million PSI, and so our yield strain is 0.00207. And so our strain in our reinforcement for grade 60 reinforcement needs to be greater than or equal to 0.0031. And that rho max equation, if we wanted to convert it to a reinforcement ratio, and we look in the TMS 402 document, rho max, our maximum reinforcement ratio, is our maximum area of steel reinforcement divided by B, our width, times D, our effective depth. And the commentary in ACI, or in TMS 402, tells us it's 0.80 times 0.80 F prime M times our strain in our masonry divided by our strain in our masonry plus alpha times our strain at yield in our reinforcement over our yield stress Fy. And so we can solve for this equation directly, but where does that equation come from? So like I mentioned, it is in our code here in TMS 402, and so this is our equation here for a fully grouted member, which the strength design provisions require beams to be fully grouted with only concentrated tension reinforcement. This is our maximum reinforcement. You'll notice there's an axial component at the end here, but for beam members, we're not allowed to have axial force on those beam members, so this term goes away, and you can see what this equation is. So where did that equation come from? Well, if we look at our strain diagram for masonry, again, our neutral axis occurs where we have zero strain on our member. And so if this is our strain diagram, this would be our neutral axis. And we have a C dimension from the top of our beam, or our point of maximum compressive stress, to our neutral axis. And this would be our strain in our masonry at the top. At the bottom, we would have our strain in our reinforcement in our tension steel. And this dimension here would be our D dimension, our effective depth to our reinforcement. And so using similar triangles, similar to ACI, we can have C divided by our strain in our reinforcement equals D divided by our strain in our masonry plus alpha times our strain at yield. And so C would be D, our effective depth, times our strain in our masonry divided by our strain in our masonry plus alpha times our yield strain. Now using our stress diagram, we know that we have at the bottom our tension force, which equals AS, our area of steel, times Fy, our yield strength. We know at the top we have our rectangular stress block that goes B dimension, the width of our beam, into the page. We know this is equal to A, which is equal to 0.8 C. And we know this is 0.80 F prime M, the width of our rectangular stress block. And so setting our masonry compressive force equal to our tension force, we get our masonry compressive force, which is 0.80 times F prime M times A times B equals our tension force equals our area of steel times our yield strength. And so our masonry force equals 0.80 F prime M times A, which we will replace A with 0.8 times C, where C equals this equation up above. And so we would have 0.80 because A equals 0.80 times C. So 0.80 D times the strain in our masonry divided by our strain in our masonry plus alpha times our yield strain. And that's times B, again, for our compression force on our section. And this needs to equal our tension force, our area of steel, times our yield strength. If we take rho is equal to AS divided by BD, so we're taking AS divided by BD on this side of the equation, so B goes away here, and D goes away from here. Then we get rho max is equal to 0.80 F prime M times 0.8 times our strain in our masonry divided by our strain in our masonry plus alpha times our yield strain, and that's divided by Fy, our yield stress, because this is our rho, AS over BD, and so we want to divide both sides by our yield stress, and we can see that this is exactly the equation that we get from the TMS 402 document for our rho max of a beam. And like I mentioned, alpha is typically 1.5 for a beam, and our yield strain is typically 0.00207 for grade 60 reinforcement, and this is 1.5. And so if we want to solve a masonry beam, the steps we're going to typically do, so step 1, we're going to solve for A, which is the depth of our rectangular stress block. And so we know our masonry compressive force is 0.80 F prime M times A times B. And so our Mn, our nominal moment capacity, needs to be M sub U divided by a theta factor, which is a strength reduction factor, which is always 0.90 for masonry and flexure, reinforced masonry and flexure. And that's going to equal 0.80 F prime M AB, our compression force, times D minus A divided by 2. And so therefore, we can solve for A, and A in this case is going to be equal to D minus the square root of D squared minus 2 times our M sub U, our moments, our factored moments, times or divided by 0.8 times phi times F prime M times B. And so as long as we know a D, a dimension effective depth to our reinforcement, M sub U, like I mentioned, is our factored moment on our section, F prime M, our compressive strength, B, the width of our beam, which is typically the width of our wall, we can solve directly for A. So then step 2, once we know what our A value is, we can solve for our required area of steel, AS required, and AS required times Fy would be our tension force. We can set that equal to 0.80 F prime M times A times B, which is our masonry compressive force. And so AS required would then be equal to 0.80 times F prime M times A times B divided by our yield stress. And once we know our required area of steel, we can select a bar size that is greater than that. So step 3, we will check our rho min. And so TMS requires a minimum amount of reinforcement in our members. And it does that by saying that our nominal moment capacity needs to be greater than or equal to 1.3 times our cracking moment. And to solve for our cracking moments, we need to know our modulus or rupture and our section modulus, because F equals M times Y divided by I. And so if we solve for our cracking moment, M cracked equals our modulus of rupture times I divided by Y. And for a rectangular section, we can solve for that directly. So I is always going to be BH cubed over 12, and our Y for a rectangular section is H divided by 2. And so we can solve directly for our cracking moment, knowing what type of mortar we have to compute our modular or our modulus of rupture. And so our nominal moment capacity needs to be greater than or equal to 1.3 times our cracking moment. And the last step, step 4, we will check rho max to make sure we are not over reinforced. And rho max, again, is equal to AS divided by BD. And that equation we derived earlier, so we would have 0.80 F prime M times B times the strain in our masonry over the strain in our masonry plus alpha times our yield strain. And we divide that by F sub Y, our yield stress. And so our rho needs to be less than or equal to rho max to ensure that we have a ductile section. And so that is just a review of the flexural provisions in the TMS 402 document. And it's important to remember that concrete beams and masonry beams are analyzed very similarly from a stress and a strain perspective, whereas concrete uses a variable phi factor that goes from 0.65 to 0.90, depending on the strain and our reinforcement. The masonry code uses a rho max factor, a maximum reinforcement ratio, and that for beams is equal to 1.5 times our yield strain, and that's all summarized in section 9.3.3.2 of the TMS 402 document. So thanks for joining. We'll have future sessions on shear and on design of lintels. Thank you.